Hello folks, my last video was blocked by the BBC. It was about this gentleman here. His name is Jim Al-Khalili, and he was discussing what nothing is, what space is, what vacuum is, and I analyzed his video. The BBC blocked it because they claimed that I borrowed or misappropriated or misused without authorization a few of their clips. These are a few of the clips that I used. Here's a quick rundown. Jim's conclusions regarding the Michelson Morley interferometer experiment. Jim's inaccurate claim that Einstein's special relativity did away with the ether. This PhD's naive and mind-boggling assertion that you must take particles popping in from the void as proven truth. Jim's clarifying that Dirac's discovery of antimatter is today known as virtual particles under quantum field theory, okay? And Jim's conclusion that we came from nothing, after he made clear throughout his presentation that nothing is made of something. Okay, I believe that I had fair use of that material because I was using it for criticism. And I was using it in the scientific context. It was pertinent to the subject matter that I was addressing. And here is what fair use I'm using to back up my claim, and that's that it's okay to parody or comment on an original work protected under fair use. Okay, examples include showing short clips of a film while reviewing that movie, which is what I did. Okay, perfectly well. Or quoting from a celebrity in order to make fun of what they said. And I did a little bit of that as well, so both of them fall squarely within fair use. Now, I could challenge the ruling. I've learned through experience, my life, that you choose your battles, okay? And I thought it was better in this case to go in there and just edit the parts that Mr. Jim Al-Khalili talked, in which he appeared, and so I simply quoted him verbatim. I just did an voiceover, and I put new images for those same segments. And so I divided the video in two parts. The first part is going to deal with the question and answers that regarding the comments that people made, from the previous video, so it's got nothing to do with Jim Al-Khalili or with the BBC. And the second video, divided them in two videos, the second video will be dealing with Mr. Al-Khalili's arguments about the vacuum. Okay, and essentially, again, I did a voice over his segments, I put new images, and I divided them in two videos. So here goes. Enjoy. Okay, let's get to our fellow today, Mr. Al-Khalili. Okay, and here's his bio. Quick introduction to who Mr. Jim Khalil is. Okay, and this fellow is a theoretical physicist. I would withhold my interpretation of that word physicist. I don't think he is a physicist at all. There is no such thing as a theoretical physicist. There's only a physicist, and like Mr. Rutherford says, and everything else is stamp collecting. So this guy's a stamp collector. That's all he is. He's an author, okay? Broadcaster, yeah. He does a lot of that. He does a lot of, what is it? Science communication, they call it. Professor of theoretical physics, again, no such thing as theoretical physics, there's only physics. Chair in public engagement in science, University of Surrey, and regular broadcaster, presenter of science on BBC, and commentator in the British media. Yeah, he's sought after, he's popular as others that have hit it big, talking about physics and to the public, making it available to the common man who's more or less interested in physics. Okay, But again, I have a different version of Mr. Al-Khalil. I'll just call him Jim or Khalil. And this is my version. I think he's a caricature of physics. Okay? He doesn't do physics. All he's done is just repeat what he's learned by rote in college. Okay? That's my version of Mr. Khalil. And I'm sorry if that offends him or anybody else. That's my honest opinion. And why? Because he's into quantum, general relativity, and string theory, all three of which are nonsense as far as physical interpretations, which is the only thing that concerns physics. We're not concerned about equations. We're not concerned about experiments, evidence, predictions. None of that has anything to do with physics. Physics, just give me the mechanism Mother Nature uses to do her invisible work. That's physics. We know the visible stuff. All that remains until we die in the upcoming extinction is tell me how this universe works, how Mother Nature does her magic. Okay? Okay, and so here he is. I think of this guy more like Marshall Applewhite. You know, this guy had a cult some time back, and they all committed suicide. Okay, they committed suicide en masse, more or less like Jim Jones did. But this guy did it because the ETs were coming to visit us. The Martians were coming, and he said, "Oh, we got to prepare ourselves for when the Martians come." And so they all committed suicide because, I don't know, they thought they would be revived by the Martians. I don't know. Anyways, you can see these two guys look quite similar in just every respect, you know, and so it's just astonishing. And yeah, Jimmy, what he does is he talks about truth. And he asks you to believe in virtual particles and how they pop into the real world from nothing. That's why I think he's a caricature of physics, and that's what I'm going to talk about today. I'm going to talk about nothing. And Jimmy's interpretation of nothing, which is essentially the catechism, taught in general relativity and quantum mechanics in college. You know, that's what they teach. You know, if you took a course in all this stuff, you'll come up to speed real quick. It's all magic, okay? I mean, if you're a rational individual. Otherwise, you just gawk like he just did there, okay? What does Khalil ask? Well, he asks a fundamental question. He asks, what is nothing? Okay? And his answer, at least his first reaction is, it's an extremely, extremely difficult question to answer. Is it? I thought all we had to do for a concept such as nothing is define the term, and then we'll know exactly what nothing is. I mean, if you define the term, we're done, right? Someone asks you, I don't know, what is love? And you say, oh, I don't know, what is love, you know? No, just define the term, you'll know what love is. That's what the word means. What is intelligence? Okay, define the term, we'll know what it means. See how simple it was all these years? And people dismiss all that as, oh, that's semantics. Oh yeah, that's what definitions are. You need definitions to do physics, and if you want to call that semantics, well, I don't know what to tell you. I mean, you know, you need definitions. You need definitions to do law. You need definitions to do medicine. You need to know what health is, what sickness is. You need to know what disease is. If you don't know what those words mean, then how are you going to do medicine? And physics is no different. You need to define your terms. What are the words of physics? Well, you need to know what an object is, what location is, what exist means, what motion means. Those are the words of physics. That's the bread and butter of physics. And if that destroys your religion, you dismiss it, oh, that's semantic. No. We need to have these words. Otherwise, you're just going to say, oh, an object. And then you start saying, well, space-time is an object, or space is or time is an object. Then you can say that anything is an object, or a thing, or an entity, or a medium. No, you got to define these terms. Otherwise, you end up saying stupid things such as that you warp time. How can you warp time? And you might say, well, that's just a figure of speech. Yeah, tell me what prevents the Earth from running out of the solar system. If you're going to say, what's warp time? Don't use an analogy. Just tell me what physical entity prevents the Earth from flying out. And what is it? Space, time. So you're warping time. So don't tell me then, oh, it's just an analogy or that's semantics. No, that's your physical interpretation, that there's a warp wall of time. So don't turn that around and then try and tell me that, oh, you were just kidding. No, it doesn't work that way. whatever mechanism you propose, that's the one we're going to take literally, okay? Okay, so what does Khalil start with? Well, he starts with the history of vacuum, essentially. And he goes over a lot of the stuff that I went in past lectures. He just skips quite quickly through a lot of them. He doesn't go in as much detail as I went through. He starts with Aristotle, and he says, well, the Greeks believe that nature abhors a vacuum. Well, that was really Aristotle. You know, if some of you watched my previous lectures, you'll find one in which I compared Aristotle against Democritus and Parmenides, and we can simulate what they're saying with these with the little game, this little puzzle, the 16 squares. And Democritus believed that there was such a thing as empty space. And what objects did, they moved into that space, and then another object moved to the other space, and so on down the line. Parmenides says there is no such thing as empty space, and more than that, he went a little further. He says there is no such thing as motion. Yeah, he said there is no such thing as motion. He did say that. That's what the Eleatics believed in. They said, look, there is no such thing as motion because there's no empty space in which to move. And I think he was a little superior to Aristotle, who said, look, objects do move. There is motion, so Parmenides is wrong, but it turns out something immediately takes up that same space. For example, water or air can take the space left by a dog. So the dog moves, but something immediately takes that space, usually air, but it could be also the ether, okay? So these guys had three different versions of what the vacuum was, okay, the way they saw the vacuum. And the only one that, what's his name, Khalil talks about is Aristotle's version, because that's the one that lasted throughout time, okay? That's the one we had all the way at least till the 17th century, where we have this man, Toricelli. Let me move these a little bit out of here for a second so that I can bring in Mr. Toricelli. Okay, what did he come up with? Well, Toricelli came up with this, the barometer, okay? And what he did, he had some mercury there. Essentially, this is how he did it. And he says, look, if you fill this thing with mercury, and you this test tube, you can think of it as a test tube, upside down test tube, and you dip it into a pool of mercury, then you'll see that the mercury column will come down and leave a little space at the top of the little test tube. And Toricelli said, hey, look, that's vacuum. That's total nothingness up there, because nothing could get in there because the mercury was in the way of anything trying to get in there. Okay, so he said, hey, you know, that's a measure of pressure, and that's where we got the barometer, okay? Well, the first thing I want to mention, like I mentioned it before, we got to put this guy into the picture. His name was Gasparo Berti, and he came 3 years before Toricelli. We should be calling the Tors Bertis or Berts or whatever. And he did it with water. He did the same experiment with water, and I explained that. You know, he plugged the hole at the top. Okay, then he just put it in the whole thing. It's like putting a straw into your bottle of water or your glass of water or whatever. And you know, there's this volume up there that's free of particles, or so they thought. This is what their argument was. And Toricelli was in contact with Gasparo. Gasparo Berti died, and Toricelli got the credit, as always happens in these cases. You know, a lot of people think that Galileo was the guy who did the experiment with the weights and so on. No, he was beaten even by his teacher, not only his teacher, but the guy he replaced at the university. Had already written a book on the subject, and even before then you had this guy from Holland, I can't remember his name now, but I've talked about him in the past. He wrote a book, and he did the experiment in Holland of dropping the weights. So, no, Galileo was not the first one to come up with that. He's famous because he was in touch with the Catholic Church, and he was put on trial, and because Newton made him famous, because Newton used his Galileo as a reference. And the same thing with this Toricelli and Berti. He's the guy who came up with the barometer. Toricelli got the credit. Okay, same Cavendish. He wasn't the guy. John Mitchell invented the Cavendish experiment. He died, and Cavendish inherited all that and got the credit. More or less, he did the experiment, but the idea was John Mitchell's. Okay, but what was the problem with that? Okay, so you had this little test tube, okay, and you evacuated the top of the test tube, and you say, oh, there's complete vacuum. We've proven that we created vacuum. And, you know, a lot of people like Descartes, he was in disagreement. He was an Aristotelian, and he said, no, there's no such thing as a total vacuum, because as soon as you create a vacuum, something fills it. What was that something? That was the ether. And so they had this thing where they said, look, you can take sound away from this. If you remove sound from a bell jar, for example, you remove air from it, you can't send sound through that because there's no air to convey the waves or particles or whatever you want to think of sound as, okay? So once you remove the air, you have no sound inside the bell jar. But it turns out that light can still go through it. This was the issue. And so if light can go through it, then hold it. You have not evacuated everything from there. You may have evacuated the air, but there's still something in there because light is going through there. What is that something? Well, it was known, or it was the idea that it was the ether, okay? This thing that the Greeks invented. And what the suggestion was that the ether permeated the glass. So you didn't really have a vacuum. What you had is this ether in there, and that's why light could still go through the glass inside that so-called vacuum and out the other end. And so this was the issue. This is what led people to say, hey, no, there's an ether. There's an ether with maybe tiny marbles, even much tinier than what we can imagine, and it goes through the interstices of the molecules. Even though they didn't have an idea of the molecules, this is how they visualized it, okay? And under the rope model, you can see that we don't need these molecules. We do not need ether. All we have is connection, the rope that is connecting two atoms within the tube. So you can have perfect vacuum in there, assuming, right? And what is the ether? Well, that ether, if you're going to replace it with something, you're going to replace it with the ropes. The ropes are not ether, but that's what these people have been pondering all these years. We're saying that what you have is a rope between two atoms inside there. And so light can go through there because light is the torsion of a rope. You got gazillions of ropes going through there. Some people want to call that an ether. Well, that's up to them. I don't use that word. I think it's a four-letter word. All I'm saying is you have perfect vacuum in the sense that you don't have atoms. You don't have molecules in there. What you have is the connections between atoms, which are the ropes. Those are the ones that convey the light or permit light to go from, through that space. Okay, so we do have an explanation. That is the explanation. Whether you believe it or not, well, that's your personal take on that. Okay, all the way till 19th century, beginning of the 19th century, even to the end, you had the ether in the minds of all these people, all these researchers. Here you have Augustin Fresnel, which I talked about in the past, and you can see that in his main paper, which was 1819, the other one came out in 1821, when he mentioned he gave the idea of how to explain polarization, which I think was a tremendous job on his part, irrespective, because we're looking at how far back in time this guy did this. And you can see in his main paper, 1819, he talks about the ether particles. Okay, so they were still into ether, and all the way from Huygens, at least, even Hooke. And all these people, they were talking about the ether because they said, look, there's got to be, if light can go through the bell jar, through that little top portion, well, there's got to be an ether. And they just kept talking about the ether for 200, almost 300 years. In fact, we've never gotten rid of the ether. Even today, like this Nobel Prize said, Mark Farland or whatever his name is, he says, look, it is the ether, what we have today. We just don't call it that because it's taboo. The word is taboo. And but ether turned into space-time. Space-time to, what is space-time? A point at each point in space, an event, which is a point at each location in space. You know, that's what an event is, a point in space-time. So what is space-time made of? Points. What are points? Bunch of particles. What is quantum? Bunch of particles. What is out there is virtual particles that come in from the void. In other words, they make part of space. We don't see it because it's part of space, but whenever the mathematician needs it, well, the particle comes into the real world, detectable, and then goes back to form part of space. What is that? It's an ether. It's a bunch of particles. And anyone who disagrees with my definition better have a good definition for the ether. My definition, bunch of particles. Keep that in mind. Okay, so what is the ether? Well, here it is, bunch of particles, okay? I've shown that in the past. What is waving there? Well, that's the so-called wave, transverse wave, longitudinal wave, whatever wave you want to think about there. What is it? The waving of the ether. What is the ether? A bunch of particles. So what's waving? A bunch of particles. Okay, that's what the ether is, and that's what quantum, what general relativity, they're all the same. They all say it's ether. And get that through your thick skull. There's no such other notion of ether than that one, bunch of particles. Okay, let's see where I'm at here. One fella tried to, or a couple fellas, tried to determine whether there was an ether. And they're famous, Michelson and Morley, okay? And they went in there and they ran an experiment with an interferometer. And they tried to find out if there is an ether all around the Earth, okay? If space is made of, or if ether fills space, either way, is there an ether out there? That was one question. The other question is, because there were two types of ether. One was a dynamic ether, and another one was so-called static ether. And I don't know how you can imagine a static ether like a stale pond, doesn't move. I can't imagine that because the ether is supposed to be in other words, the wave is supposed to be the vibration of the ether. So if you have all these waves of light coming through, the whole ether must be vibrating. And so how can they talk about a static ether? And nevertheless, they had these two visions, the static ether and the dynamic ether. One is a river or an ocean with waves and everything. The other one is the static, bunch of particles and the earth just plowing through it. Okay, so we have two types of ether in the minds of the 19th centuryers, right? And two guys trying to figure out if there was such a thing as the ether. And here's Jim Al-Khalili's version of the interferometer that was used to determine that there was no ether. So here's, in a nutshell, how this was proven to the mathematicians of those days. Okay, let me set it in motion. It's an MP4, so give me a second here, and I'll keep my mouth shut so you can hear it. There it goes. Because of the wave-like properties of light, you see a very specific pattern here. Basically, if the light just traveled at the same speed along two paths, then you see a bright spot in the middle of the pattern. Let's look at what happens when we simulate the effects of an ether. The light leaves the detector and gets split. Now here's the key. The light that travels against the ether and back again covers this journey in a different time to the light traveling across the ether. This means that when the light waves recombine, they now interfere with each other. This interference means that the image will have a dark spot at its center. See this, and you know that the void must be filled with a stationary medium through which the Earth is moving. Essentially, these are where the differences with and without ether. Okay, there you see it. Constructive interference, no ether. Destructive interference, that means the Earth is moving through the ether. And so what they found out is that there was no ether, according to their experiment. Now, I don't want to put words again in the mouths of Michelson and Morley because there's a lot of debate on what they really interpreted. The point here is that all the mathematicians in those days came up with the notion that there was no ether. The ether started dying very quickly. And one of the problems that created is that that's where we started with time dilation. Because of that experiment, because of this null version of the ether. And so you have people like Fitzgerald who started questioning that, and Irish guy, and he said no, then there's got to be an ether. He didn't want to let go of the ether, but then he said what we have here is just a question of time. And so eventually they came up, Lorentz came up with his equation where he says, okay, I know what's happening there. What's happening there is, here's the equation. He showed his little equation where it shows that it's a question of perception. It's that the apparatus, as Fitzgerald said, is shrinking in the direction of motion. In other words, the interferometer was squishing. Or the light coming out of the interferometer, there were different interpretations on that as well. So that's where they started with time dilation and length contraction. That's where it started, but eventually it led to all this mass increase that Einstein included in his special relativity. So the issue was that, the bottom line here was that slowly the ether died after 300 years. At the end of the 19th century, beginning of the 20th, maybe about 1910, 1920, the ether was pretty much dead in the minds of most mathematicians. A new generation of mathematicians had taken over and overthrown the previous regime, essentially, the old folks. They or like someone says, theories die when the old folks die. Okay, so that's Jim Al-Khalili's version of Michelson Morley experiment. You get an idea. There was simply a difference between the speeds of light if there was an ether out there, and they showed that there was no interference. Okay, that was the bottom line. Okay, so Einstein comes up a few years later. About 1900. They say he says 1905. I think it was 1908. Okay, because Einstein came up with the notion that that you don't need an ether. Actually, that's debated even to today. The interpretation today is that Einstein invented a new or a different kind of ether. Okay, here's Khalili's version of Einstein's debunking of the ether. Again, I'm going to turn it into, turn the MP4 on, and here it goes. So how does light move through empty space? Well, by the end of the 19th century, light was known to be a fact of combination of fluctuating electric and magnetic fields. It would take the genius of Einstein in 1905 to reveal that this picture of light doesn't need an ether. He showed that it has the weird property of being able to propagate through completely empty space. Maybe the vacuum is really empty. If only it were that simple. Okay, and yeah, here you see a statement. Remember one thing, this is how Khalili presents Einstein, but I'm not sure he's being presented in the proper light. First of all, in 1915, Einstein, by that time, he wasn't the only guy. Really, it was a lot of other people, among them Minkowski, who came up with this notion of space-time. It wasn't Einstein, but it also came from other people even before Minkowski. And Einstein essentially came up with this theory, and he usurped that term, and everybody gives him credit for space-time. But what is space-time? Space-time is an ether. It's something out there that fills space, or better yet, it is space in space and time in the case of Einstein's theory. But that was in 1915 to 1916. That's where they were developing these ideas. And here's good old Einstein in 1920. And this is a famous address he gave at the University of Leiden. And here it is. And what does he say? Well, he says, we may say, according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable. Okay, now why didn't Al-Khalili mention that? When it's well known that Einstein insisted on the ether, to the end of his life, because what is space-time? Space-time is an ether. It's a something, not a nothing. They didn't talk about empty space. They talked about filled space, or space being something, an entity, a medium, a physical medium. What did he just say? Endowed with physical qualities, physical properties. Okay, so yeah, you can't avoid it. All these people, all the mathematicians, since the days of the Greeks, no one has changed that. Everyone thinks space is something, or it's made of something, or it's filled with something. Filled meaning every little bit of space. And again, you say, if that's the case, if space is filled with particles, what contours each space particle? What contours each particle of ether? That's what we want to know. And hopefully you say, well, space. Nothing. Yeah, it's got to have a backdrop. You're going to talk about particles, and that's the issue. Nobody has defined the word object, what an object is, and that's where we start with a problem. Okay, Einie was overthrown as well. Good old Einstein. Time went by, and some other people came around, and one of them was Paul Dirac, according to Al-Khalili. And what did Paul Dirac come up with? Well, he came up with antiparticles, what is going to be known as the positron. You have the electron, which is negative charge, which is a little bead that goes around the atom. We don't know why it's negative, or we don't know what negative means. It's just negative because the positron is positive, and also because the proton was positive. So the first notion was this notion created by Rutherford, saying, look, the proton is positive and the electron is negative. And those words come really from Ben Franklin 200 years earlier, 100 years earlier than them. But the point is, they had this electron marble that was negative, whatever that meant in physics, just mathematical gibberish. And now Paul Dirac, in 1928, he comes up there and says, look, the electron has a counterpart, and it's the positron. And if they come together, they annihilate, and you release all this kind of energy. And so the search was on to find a positron, and you had this fellow, Carl Anderson. He's going to discover it a few years later. They discover all these things. And I got a lot to say about what Carl Anderson did, really, but I put that in my site, but I'm not going to talk about that today. Anyways, Paul Dirac said, look, there's something called an anti-electron, otherwise known as a positron, otherwise known as antimatter. You have matter on the one side, antimatter on the other side, and hopefully they never come together. Like two Bill Gates, a positive and a negative Bill Gates, they annihilate if they, lots of energy there. Anyways, this is Al-Khalili's version of Paul Dirac's discovery, right? And again, it's an MP4, so here it goes. I'll keep my mouth shut.
Here, finally, was the answer to the riddle of empty space. Heisenberg's uncertainty principle had suggested that matter could pop into existence for incredibly short periods of time. Now, Dirac had provided the mechanism by which matter could be created out of the vacuum, and just as quickly disappear again. Whenever a particle pops out of empty space, so simultaneously does its antiparticle. Although this sounds completely ridiculous, let me assure you that it is true.
So you have all these particles now not only popping out of the void, out of nothingness, out of the vacuum, out of space, but they've turned these particles into virtual particles. In other words, they say, look, these particles, I guess, make up space. That's the notion these people have. And so they say, look, space is made out of particles, or it's filled with all these particles. And by filled, they mean every little space. And if the particles are round, I want to know what's between two round particles. You know, you can't have three particles together and occupy all the space. No, there's got to be some space between them. And if they're particles, something has to contour each particle anyways. What is that something? That's what we want to find out. And they never address that issue. They just say, oh, they pop in from the void because that's what we see in the laboratory. Well, that's their interpretation. They can't see this stuff, so they say it popped in from the void. Okay, good solution. I mean, we might as well use spirits. The spirit popped in from the void, moved my curtain, and went back out. So I've got an explanation for why the curtain moved, see? I mean, these are the type of answers these people are giving you. And here we have the version of how it became, in other words, how that anti-electron, positron, whatever you want to call it, became a household name, okay? And let me set this up. Again, an MP4. Here it goes.
Dirac's theory of the electron and the idea of antimatter gives us a completely new picture of the vacuum. Before, you could think about vacuum as just empty space, so to speak. Relativity had said you don't need an ether. So, the picture was of the vacuum being empty. But when you bring relativity and quantum theory together, then you have for certain this notion of electron and anti-electron pairs just appearing out of the vacuum.
Yeah, particles appearing out of the vacuum. That's what a mathematician says today. Now tell me how much different that is when the old folks in the old days, 500 years ago, they said, oh, the spirit came out of nowhere and whoo, just scared the hell out of me. Yeah, this is the same thing. It's presented in the guise of science, but make no mistake. What you're staring at is a bunch of religious folk who have taken over science. They call themselves atheists. They say they're rational. They say they're logical. They say they're smart because intelligent because they do equations. And they come up with all these mathematical descriptions. And then they come up with such idiocy like saying particles appear from the void. What are you supposed to think of them? Give them a Nobel Prize? Yeah, give them all the prize. I mean, what is the Nobel Prize? A beauty contest? Olympics medal? What is that? We give prizes for intelligence now? Only makes matters worse because people are worried more about winning the medal than about making sense. Okay, and here are another version of how Dirac's idea progressed over time, even to these days as we have it today. We'll see here how Al-Khalili presents Paul Dirac's discovery of the positron, of the antimatter, anti-electron. So let me get that rolling as well.
Dirac's ideas about empty space were refined and developed in what is known today as quantum field theory. And these strange fleeting things within nothing became known as virtual particles.
So what is the danger with all this? You might say, well, what's the harm? Well, let me tell you what the harm is. The harm is that these people have a total erroneous version of how the universe works. And one of those big erroneous things is, you know, the traditional religion say, hey, you know, so how did the universe come to be? If you say that the universe, if you take the film back and you say, hey, you know, if all these galaxies are separating from each other, then in the past they were closer together, and we go way, 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 way into the past, 14 billion years. we get them all lumped together. And they say, oh, there was a big explosion. We'll call it the Big Bang. And so, you know, the religious folk, the traditional religious folk, because these guys are religious as well, they said, okay, so how did it start? What came before the Big Bang? How did it all start? And these people say, okay, Paul Dirac gave us the clue. The way it all started is, you know, you can create matter from the void, whatever the void is, right? Because we don't know what the void is, but it turns out the void is just two particles, an electron and a positron, or matter, antimatter, anyway, any words that you want to use. You have two particles that, you know, a black ball and a white ball, when they get together, they form a no ball. And when they separate, well, you have a black ball and a white ball, right? And that's more or less what these people are saying. They're saying, no, you got a virtual particle, but where are they? Well, you have these positrons and electrons. They separate. When they're together, they form nothing, whatever nothing is, because we don't. It's a particle of nothing. And then when they separate, well, then you have some action in the real world, and they immediately go back. They borrow the energy momentarily, and then they go back to being nothing again, which is a particle of nothing. That's their explanation. And why is that a problem? Well, again, because they tell you that they know not only that the universe began 14 billion years ago, but now they have a scientific mechanism for how the universe came to be, from nothing. Because the vacuum is not really nothing. What is the vacuum? The vacuum is two particles that form a particle of nothing, which is contoured by who knows what. By anything, by nothing, by something, I don't know. Okay, and so I've got, let's see, is it? Yeah. Here's the part where he explains that how the universe came to be from nothing. This is, if you always wanted to know how the universe came to be, how the Big Bang got started, here it is, you know. Here it goes.
At the beginning of time, the universe sprang from the vacuum, creating not only vast amounts of matter, but also antimatter. But the universe we see today is made of matter. Nearly all of the antimatter seems to have vanished.
So now you know how the universe got started. All you had is negative and positive particles, and when they got together, they had neutral particles, zero particles, or particles with a zero subscript instead of a positive or a negative sign. Is that how the universe got started? So we separate the particle sub-zero, and it turns into a particle sub-negative and a particle sub-positive. That's how it's explained today. So yeah, these people say, hey, you have God, but who made God? See, we can tell you how the universe got started. You can't, because you can't explain the existence of God. But we can. We had nothing, whatever nothing is, which is a particle that is composed of positive and negative. When they're together, they form nothing. And when they separate, we have something. And we have matter and antimatter. But it turns out that for some unknown reason that they're still researching, they don't have an answer to this, why there is more matter than antimatter, or why there's no antimatter at all. And they say, well, for some reason, you know, when they separated, there was the same quantity, but then after a while, some matter was left over, and they can't explain it yet, but they'll find an answer sometime in the future, why there's one more particle of matter than of antimatter in the universe, or why there's no antimatter unless you create it in the lab or whatever. So they have all these irrational explanations, essentially. But here is Hawking's version of that same thing, and I'll just read it to you here real quick. It says, at the Big Bang itself, the universe is thought to have had zero size, and so to have been infinitely hot, okay? There's something like blah, 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 a bunch of numbers there, a one with 80 zeros after it, particles in the region of the universe that we can observe. Where did they all come from? The answer is that in quantum theory, particles can be created out of nothing. They call it energy, okay, in the form of particle-antiparticle pairs. See, just now you heard Khalili say they came out of nothing. This guy says, no, it came out of energy. Whatever. So I guess energy is nothing, right? And what is it? It's in the form of particle-antiparticle pairs, and those form nothing. Now, nothing called energy, or energy called nothing. But that just raises the question of where the energy came from. And here, this is the hocus pocus. He says the answer is that total energy of the universe is exactly zero, okay, except for the antimatter, which apparently matter is a little more numerous than antimatter. The matter in the universe is made out of positive energy. The gravitational field has negative energy. In the case of the universe that is approximately uniform in space, one can show that this negative gravitational energy exactly cancels the positive energy represented by the matter, so the total energy of the universe is zero. Now, twice zero is also zero, okay? Thus, the universe can double the amount of positive matter energy and also double the negative gravitational energy without violation of the conservation of energy. When the universe doubles in size, the positive matter energy and the negative gravitational energy both double. So the total energy remains zero. The universe is the ultimate free lunch. They had to turn all this around, because the religious folks were saying, hey, you so-called scientists, you don't know the answer either. And they say, oh, yes, we do. See, we have a scientific proof, equations, proof, experiments, predictions. They predict the past. We've got all that. You got nothing. You got God, and you can't tell me who made God. But see, we know how something came out of nothing. And there was this energy, you see. So how did the energy come in there? Well, we don't have to explain that, because you have positive and negative energy. When they come together, they form energy sub-zero, no energy, I don't know. Zero energy, they say. So they have all this mathematical gibberish, and they try to explain the origin of the universe through this hocus pocus, which is no different than the traditional religions. But a lot of people buy it. They say, oh, that's scientific. Especially the atheists buy that, like candy. Okay, so what does Mr. Khalili conclude after all that talk? He has an hour video on this nothingness. You should watch it. It's interesting, the way they think. And so this is his final comment. He says, look, we started out with Aristotle, and he said, look, there is really no such thing as space, or maybe there is, but something fills that space immediately. Rene Descartes, all the way into the 16th century, said the same thing. He says, look, something moves, something else takes its place. And when it wasn't air or water, they said, then what happens inside the little vacuum tube? He says, then that's the ether that fills that space, because we can't hear the noise because we've taken all the air out, so there's no molecules or atoms or anything macro in there, but there's still something in there, and that's because light can go through that same space, and that's what they call the ether. That's how the ether lasted all the way to today. Okay, we still have the ether, because they can't explain that phenomenon unless you know what light is. Okay, so if you're going to do it with particles, you say, well, are the particles going right through the glass? Yes, they are. That means that whole top of the bell jar is filled with ether. That is the current version. They just call them virtual particles, or who knows what kind of particles, positive, negative particles, but it's an ether. That's all it is. It's an ether theory. Okay, so these are his conclusions, Jim Al-Khalili's conclusions. And let me get this in here. Here it goes. Go.
What we once thought of as the void now seems to hold within it the deepest mysteries of the entire universe. We've uncovered the strange truth about reality itself. There's a profound connection between the nothingness from which we originated and the infinite in which we're engulfed.
The nothing from which we originated. I thought there was no such thing as nothing, because he just showed that the nothing is made of something. And so this takes me to my conclusions. I can only share them with you. The fatal problems with Jim Al-Khalili's proposal. And here they are. These are my objections to his notion of nothingness. These are some. I have a lot more than this, believe me. But I've just put the most important ones that I want you to think about. First, he failed to define a thing to begin with. He doesn't tell us what a thing is, and he goes in there and says, and now I'm going to talk about nothing, no thing. He fails to define nothing as well. He doesn't tell me what nothing means, so we don't know what his entire argument is, because he ends up saying that nothing is something. In other words, nothing is made of particles. And that sounds like something. That doesn't sound like nothing to me. Like nothing is when you don't have particles, but if you have particles in there, making up or filling that space, for lack of a better word, then what is this nothing that you're talking about? So you got to define these terms. Otherwise, you can't talk sensibly. In rational science, very straightforward. Thing or something, that which has shape. Nothing, for practical purposes, that which doesn't have shape. Very simple. Straightforward. Antonyms, you can use them consistently. We're done. No semantics, no gibberish, no nothing. Straightforward. But then here are some questions. If the space is made of particles that pop into the detectable world at random, what medium provides contrast to these particles when they disappear back and form space again? I mean, what contours each particle? That's what we want to know. Don't tell me that positive goes with negative and it turns to zero. Yeah, that's great. Fine. We don't care. We want to know what contour. I mean, we're talking physics here, right? So we don't care about if positive, negative, zero. That doesn't enter the picture. Mother Nature doesn't understand that gibberish. What she understands is, what physics, which is what contours each particle. That's what we want to know. That's what we want to understand from your theory. Does a virtual particle leave a hole behind in space when it momentarily comes into our detectable world? I mean, if this particle came out, what did it leave behind? A hole? A hole in space? What is space? What is nothing? Again, it goes back to the definition. You need to define this term. You need to tell us what you're talking about. They don't do that. So whenever one of these guys approaches you, just tell them, hey, I want you to define the word space, nothing, vacuum. I want a definition before we start our discussion, because otherwise you're just going to go around in circles. You're going to say, oh, we have the scientists, the physicists proved that space is made of virtual particles that pop in from the void. No, tell me what space is. Tell me what nothing is. Give me a definition. Tell me if it's a physical object, a standing object. Tell me whether particles fill space or the particles are space. Is space made of particles, or do particles fill this container called space? That's got to be clarified. Otherwise, you're not going to understand, you're going to be chasing your tail around in the discussion. Last one there, a couple. Why is there more matter than antimatter, or no antimatter at all? And they're searching for an answer. They don't know why there's more matter today than antimatter, for example. Some people say there is no antimatter. Others say, well, there is some that we create in the lab, but it immediately recombines with matter and it annihilates and creates all this energy. Okay, and then space is a physical object. Does it have boundaries? Hopefully, it does if it's a physical object. And then the only question there is, what's outside of space giving it shape, boundaries? So yeah, and of course at that point is when they dismiss your stuff as semantics or philosophy, and they say, well, you're doing philosophy, Bill. Now it goes to the root of what they're trying to explain. Their whole theory falls apart with these type of problem. Anyways, I won't see you on Sunday because it's my youngest son's birthday. He's turning 30, big day, and so we're going to be celebrating his birthday. So I'll see you next Wednesday, folks. We'll see you then. Bye-bye.